Hello everyone. The topic that we are going to read today is states of matter. I'll be dividing this chapter into two parts, part 1 and part 2. Since the chemistry chapters are quite long, so you'll be getting in parts, whereas all the bio chapters, whether it is of 11th or class 12th, it is just one single video uploaded. So you can check out the playlist and all the chapters are uploaded and you can refer the audiobook. So without wasting any time, let's get started. States of Matter. Part 1. Introduction. In the previous units, we have learnt about the properties related to single particle of matter, such as atomic size, ionization enthalpy, electronic charge density, molecular shape and polarity, etc. Most of the observable characteristics of chemical systems with which we are familiar represent bulk properties of matter. That is, the properties associated with a collection of a large number of atoms, ions, or molecules. For example, an individual molecule of a liquid does not boil, but the bulk boils. Collection of water molecules have wetting properties, individual molecules do not wet. Water can exist as ice, which is a solid. It can exist as a liquid, or it can exist in the gaseous state as water vapor or steam. Physical properties of ice, water, and steam are very different. In all the three states of water, chemical composition of water remains the same, that is H2O. Characteristics of the three states of water depend on the energies of the molecules and on manner in which water molecules aggregate. Same is true for the other substances also. Chemical properties of a substance do not change with the change of its physical state, but rate of chemical reactions do depend upon the physical state. Many time in calculations, while dealing with data of experiments, we require knowledge of the state of matter. Therefore, it becomes necessary for a chemist to know the physical laws which govern the behavior of matter in different states. In this unit, we will learn more about these three physical states of matter, particularly liquid and gaseous states. To begin with, it is necessary to understand the nature of intermolecular forces, molecular interactions, and effect of thermal energy on the motion of particles because a balance between these determines the state of a substance. Intermolecular forces. Intermolecular forces are the forces of attraction and repulsion between interacting particles, that is, atoms and molecules. This term does not include the electrostatic forces that exist between the two oppositely charged ions and the forces that hold atoms of a molecule together, that is, covalent bonds. Attractive intermolecular forces are known as van der Waals forces, in honor of Dutch scientist Johannes van der Waals, who explained the deviation of real gases from the ideal behavior through these forces. We will learn about this later in this unit. Van der Waals forces vary considerably in magnitude and include dispersion forces or London forces, dipole-dipole forces, and dipole-induced dipole forces. A particularly strong type of dipole-dipole interaction is hydrogen bonding. Only a few elements can participate in hydrogen bond formation. Therefore, it is treated as a separate category. We have already learnt about this interaction in Unit 4. At this point, it is important to note that attractive forces between an ion and a dipole are known as ion dipole forces, and these are not van der Waals forces. We will now learn about different types of van der Waals forces. Dispersion forces or London forces. Atoms and nonpolar molecules are electrically symmetrical and have no dipole moment because the electronic charge cloud is symmetrically distributed. But a dipole may develop momentarily even in such atoms and molecules. This can be understood as follows. Suppose we have two atoms A and B in the close vicinity of each other. It may so happen that the momentarily electronic charge distribution is one of the atoms, say A, becomes unsymmetrical. That is, the charge cloud is more on the one side than the other, as shown in figure 5.1 B and C. This results in the development of instantaneous dipole on the atom A for a very short time. This instantaneous or transient dipole distorts the electron density of the other atom B, which is close to it, and as a consequence, a dipole is induced in the atom B. The temporary dipoles of atoms A and B attract each other. Similarly, temporary dipoles are induced in molecules also. This force of attraction was first proposed by German physicist Fritz London. And for this reason, force of attraction between two temporary dipoles is known as London force. Another name for this is dispersion force. These forces are always attractive, and interaction energy is inversely proportional to the sixth power of the distance between two interacting particles, that is 1 by r raised to 6, where r is the distance between two particles. These forces are important only at short distances, that is 500 pm, and their magnitude depends on the polarizability of the particle. Dipole-dipole forces. Dipole-dipole forces act between the molecules possessing permanent dipole. Ends of the dipole possesses partial charges, and these charges are shown by Greek letter delta. Partial charges are always less than the unit electronic charge, 1.6 into 10 raised to minus 19 coulomb. The polar molecules interact with the neighboring molecules. Figure 5.2a shows electron cloud distribution in the dipole of the hydrogen chloride. And figure 5.2b shows dipole-dipole interaction between two HCl molecules. This interaction is stronger than the London forces, but it is weaker than the ion-ion interaction because only partial charges are involved. The attractive force decreases with the increase of distance between the dipoles. As in the above case, here also the interaction energy is inversely proportional to the distance between polar molecules. Dipole-dipole interaction energy between stationary polar molecules, as in solids, is proportional to 1 by r raised to 3, and that between rotating polar molecules is proportional to 1 by r raised to 6, where r is the distance between polar molecules. Besides dipole-dipole interaction, polar molecules can interact by London forces also. Thus, cumulative effect is that the total of the intermolecular forces in polar molecules increase. Dipole-induced dipole forces. This type of attractive forces operate between the polar molecules having permanent dipole and the molecules lacking permanent dipole. Permanent dipole of the polar molecule induces dipole on the electrically neutral molecule by deforming its electronic cloud. Thus, an induced dipole is developed in the other molecule. In this case also, interaction energy is proportional to 1 by r raised to 6, where r is the distance between two molecules. Induced dipole moment depends upon the dipole moment present in the permanent dipole and the polarizability of the electrically neutral molecule. We have already learnt in Unit 4 that molecules of larger size can be easily polarized. High polarizability increases the strength of attractive interactions. In this case also, cumulative effect of the dispersion forces and dipole-induced dipole interaction exist. Hydrogen bond. As already mentioned in section 5.1, This is a special case of dipole-dipole interaction. We have already learnt about this in Unit 4. This is found in the molecules in which highly polar NH, OH, or HF bonds are present. Although hydrogen bonding is regarded as being limited to nitrogen, oxygen, and fluorine, but species such as Cl- may also participate in hydrogen bonding. Energy of hydrogen bond varies between 10 to 100 kilojoule per mole. This is quite a significant amount of energy. Therefore, hydrogen bonds are powerful force in determining the structure and properties of many compounds. For example, proteins and nucleic acids. Strength of the hydrogen bond is determined by the Coulombic interaction between the lone pair electrons of the electronegative atom of one molecule and the hydrogen atom of the other molecule. Following diagram shows the formation of hydrogen bond. Intermolecular forces discussed so far are all attractive. Molecules also exert repulsive forces on one another. When two molecules are brought into close contact with each other, the repulsion between the electron clouds and that between the nuclei of two molecules come into play. Magnitude of the repulsion rises very rapidly as the distance separating the molecule decreases. This is the reason that liquids and solids are hard to compress. In these states, molecules are already in close contact. Therefore, they resist further compression as that would result in the increase of repulsive interactions. Thermal energy. Thermal energy is the energy of a body arising from motion of its atoms or molecules. It is directly proportional to the temperature of the substance. It is a measure of the average kinetic energy of the particles of the matter and is thus responsible for movement of particles. This movement of particles is called thermal motion. Intermolecular forces versus thermal interactions. We have already learned that intermolecular forces tend to keep the molecules together, but thermal energy of the molecules tend to keep them apart. Three states of matter are the result of a balance between intermolecular forces and the thermal energy of the molecules. When molecular interactions are very weak, molecules do not cling together to make liquid or solid unless thermal energy is reduced by lowering the temperature. Gases do not liquefy on compression only, although molecules come very close to each other and intermolecular forces operate to the maximum. However, when thermal energy of the molecule is reduced by lowering the temperature, the gases can be very easily liquefied. Predominance of thermal energy and the molecular interaction energy of a substance in three states is depicted as follows. So here you can see the depiction where the predominance of intermolecular interaction and thermal energy is given. We have already learned the cause for the existence of the three states of matter. Now we will learn about gaseous and liquid states and the law which govern the behavior of matter in these states. We shall deal with the solid state in class 12th. The gaseous state. This is the simplest state of matter. Throughout our life, we remain immersed in the ocean of air, which is a mixture of gases. We spend our life in the lowermost layer of the atmosphere called troposphere, which is held to the surface of the earth by gravitational force. The thin layer of atmosphere is vital to our life. It shields us from harmful radiations and contains substances like dioxygen, dinitrogen, carbon dioxide, water vapor, etc. Let us now focus our attention on the behavior of substances which exist in the gaseous state under normal conditions of the temperature and pressure. A look at the periodic table shows that only 11 elements exist as gases under normal conditions, as it is shown over here in figure 5.4. You can see hydrogen, nitrogen, oxygen, fluorine, chlorine, and the noble gases. The gaseous state is characterized by the following physical properties. Gases are highly compressible. Gases exert pressure equally in all directions. Gases have much lower density than the solids and liquids. The volume and the shape of gases are not fixed. These assume volume and shape of the container. Gases mix evenly and complete in all proportions without any mechanical aid. Simplicity of gases is due to the fact that the forces of interaction between their molecules are negligible. This behavior is governed by same general laws, which were discovered as a result of the experimental studies. These laws are a relationship between measurable properties of gases. Some of these properties like pressure, volume, temperature and mass are very important because the relationship between these variables describes state of the gas. Interdependence of these variables lead to the formulation of gas laws. In the next section, we will learn about gas laws. The gas laws. The gas law which we will study now are the result of research carried on for several centuries on the physical properties of gases. The first reliable measurement on properties of gases was made by Anglo-Irish scientist Robert Boyle in 1662. The law which he formulated is known as Boyle's law. Later on, attempts to fly in air with the help of hot air balloons motivated Jacques Charles and Joseph Louis Gay-Lussac to discover additional gas laws. Contribution from Avogadro and other provided lot of information about gaseous state. Boyle's law, pressure-volume relationship. On the basis of his experiment, Robert Boyle reached to the conclusion that at constant temperature, the pressure of a fixed amount, that is number of moles N, of a gas varies inversely with its volume. This is known as Boyle's law. Mathematically, it can be written as P is directly proportional to 1 by V at constant temperature and N. P is equal to K1 1 by V, where K1 is the proportionality constant. The value of constant K1 depends upon the amount of the gas, temperature of the gas, and the units in which pressure and volume are expressed. On rearranging equation, we obtain PV is equal to K1. It means that at constant temperature, product of pressure and volume of a fixed amount of gas is constant. If a fixed amount of gas at constant temperature occupying volume V1 at pressure P1 undergoes expansion so that volume becomes V2 and pressure becomes P2, then according to Boyle's law, P1 V1 is equal to P2 V2 is equal to constant. Therefore, P1 upon P2 is equal to V2 upon V1. So here you can go through the graphs because these graphs are very important as exam point of view. So the graph of which is pressure volume graph, and here also you can see where temperature is shown, where T3 greater than T2 and T1. So that is important. Okay. Figure 5.5 shows two conventional ways of graphically presenting Boyle's law. Figure 5.A is the graph of the equation 5.3 at different temperatures. The value of K1 for each curve is different because for a given mass of gas, it varies only with temperature. Each curve corresponds to a different constant temperature and is known as an isotherm, constant temperature plot. Higher curves correspond to higher temperature. It should be noted that volume of the gas doubles if the pressure is halved. Table 5.1 gives effect of pressure on the volume of 0.09 mole of CO2 at 300 Kelvin. Figure 5.5b represents the graph between P and 1 by V. It is a straight line passing through origin. However, at high pressures, gases deviate from Boyle's law, and under such condition, a straight line is not obtained in the graph. Experiment of Boyle's in a quantitative manner prove that gases are highly compressible because when a given mass of gas is compressed, the same number of molecules occupy a smaller space. This means that gases become denser at higher pressure. A relationship can be obtained between density and pressure of a gas by using Boyle's law. By definition, density D is related to mass m and the volume V by relation D is equal to m by V. If we put value of V in this equation from Boyle's law equation, we obtain the relationship. D is equal to m upon K1 into P is equal to K dash P. This shows at a constant temperature, pressure is directly proportional to the density of a fixed mass of the gas. Charles' law, temperature-volume relationship. Charles and Gay Lussac performed several experiments on gases independently to improve upon hot air balloon technology. The investigations showed that for a fixed mass of gas at constant pressure, volume of a gas increases on increasing temperature and decreases on cooling. They found that for each degree rise in temperature, volume of a gas increases by 1 by 273.15 of the original volume of the gas at 0 degrees Celsius. Thus, if volumes of the gas at 0 degrees Celsius and at T degrees Celsius are V0 and Vt respectively, then Vt is equal to V0 plus T upon 273.5 into V0. So here you can see the derivation for Charles' law and how finally V total Vt is equal to V0 273.15 plus T upon 273.15 the whole is found out. At this stage, we define a new scale of temperature such that T degrees Celsius on new scale is given by T is equal to 273.15 plus T and 0 degrees Celsius will be given by T0 is equal to 273.15. This new temperature scale is called the Kelvin temperature scale or absolute temperature scale. Thus, 0 degrees Celsius on the Celsius scale is equal to 273.15 Kelvin at the absolute scale. Note that the degree sign is not used while writing the temperature in absolute temperature scale. Kelvin scale of temperature is also called thermodynamic scale of temperature and is used in all scientific works. Thus, we add 273, more precisely 273.15 to the Celsius temperature to obtain temperature at Kelvin scale. Thus, if we write T total is equal to 273.15 plus T and T naught is equal to 273.15 in the equation and you get the relationship. So I don't think so there is need to read all this stuff. Only important, if you ask me like what is important in this chapter, we should know the relationships and certain terminologies like what is dispersion force, London forces and all, because this already derivation and all is already done for your boards and it is not much required for your NEET. In NEET आपको वही question solve करने आना चाहिए. Okay. Equation 5.10 is the mathematical expression for Charles' law, which states that pressure remaining constant, the volume of a fixed mass of gas is directly proportional to its absolute temperature. Okay? Charles found that for all gases at any given pressure, graph of volume versus temperature in Celsius is a straight line, and on extending to zero volume, each line intercepts the temperature axis at 273.15 degrees Celsius. Slopes of lines obtained at different pressure are different, but a zero volume of all the lines meet the temperature axis at 273.15 degrees Celsius. Each line of the volume versus temperature graph is called isobar. Observation of Charles can be interpreted if we put the value of T in equation as minus 273.15 degrees Celsius. We can see that the volume of the gas at minus 273.15 degrees Celsius will be 0. This means that gas will not exist. In fact, all the gases get liquefied before this temperature is reached. The lowest hypothetical or imaginary temperature at which gases are supposed to occupy zero volume is called absolute zero. All gases obey Charles' law at very low pressures and हाई टेम्परेचर. तो इम्पॉर्टेंट लाइन ये है कि चार्ल्स लॉ कब फॉलो होता है, लो प्रेशर पे एंड हाई टेम्परेचर्स पे. ठीक है. Gay-Lussac's law, pressure-temperature relationship. Pressure in well-inflated tires of automobiles is almost constant. But on a hot summer day, this increases considerably and the tire may burst if pressure is not adjusted properly. During winters on a cold morning, one may find the pressure in the tires of a vehicle decreased considerably. The mathematical relationship between pressure and temperature was given by Joseph Gay-Lussac and is known as Gay-Lussac's law. It states that at constant volume, pressure of a fixed amount of gas varies directly with the temperature. Mathematically, P is directly proportional to the temperature. P upon T is equal to constant is equal to K3. This relationship can be derived from Boyle's law and Charles' law. Pressure versus temperature Kelvin graph at constant molar volume is shown in figure 5.7. Each line of this graph is called isochore. तो ये ग्राफ आप देख पा रहे हो, ठीक है. दिस ग्राफ अगेन बिकम्स इम्पोर्टेंट. ग्राफ से भी बहुत बार क्वेश्चन पूछते हैं, तो अगेन इट बिकम्स इम्पोर्टेंट. Avogadro law volume amount relationship. In 1811, Italian scientist Amedeo Avogadro tried to combine conclusion of Dalton's atomic theory and Gay-Lussac's law of combining volumes, which is now known as Avogadro law. It states that equal volumes of all gases under the same conditions of temperature and pressure contain equal number of molecules. This means that as long as the temperature and pressure remain constant, the volume depends upon the number of molecules of the gas, or in other words, the amount of gas. Mathematically, we can write V is directly proportional to N, where N is the number of moles of the gas. V is equal to K4N. The number of molecules in 1 mole of a gas has been determined to be 6.022 into 10 raised to 23 and is known as Avogadro constant. You will find that this is the same number which we came across while discussing definition of a mole in unit 1. Since volume of gas is directly proportional to the number of moles, 1 mole of each gas at standard temperature and pressure STP will have same volume. Standard temperature and pressure means 273.15 Kelvin or 0 degree Celsius temperature and 1 bar, that is exactly 10 raised to 5 Pascal pressure. These values approximate freezing temperature of water and atmospheric pressure at sea level. At STP, molar volume of an ideal gas or a combination of ideal gas is 22.7198 liter per mole. Molar volume of some gases is given, you can see in the table below. So here you can see argon, carbon dioxide, but generally हम लोग, आपको तो पता है कि कैलकुलेशन के लोग 22.7 डायरेक्ट ले लेते हैं. Number of moles of gas can be calculated as follows. N is equal to small m upon capital M, where mass of the gas under investigation and capital M is the molar mass. ठीक है, तो ये आप लोग देख लेना इक्वेशन. देखो इक्वेशन रीड करके कुछ मतलब नहीं है, वो आपको खुद पता होना चाहिए और खुद आना चाहिए. मैं सिर्फ रीड कर दूंगी, आपके दिमाग में से वैसे नंबर्स चलेगा, कुछ मतलब मुझे नहीं लगता ये कुछ हेल्पफुल रहेगा. हाँ, टेक्स्ट बुक के जो इम्पोर्टेंट स्टेटमेंट्स है, अभी तक तो मैंने रीड नहीं किया, लेकिन जब मैं रीड करूँगी तो जो भी इंपॉर्टेंट स्टेटमेंट्स है मैं उसका पूरा एक प्रॉपर बोलते हैं ना, आई विल राइट डाउन ऑल द इम्पॉर्टेंट स्टेटमेंट्स एंड चाहिए तो फिर मैं वो अपलोड कर दूँगी. ठीक है. A gas that follows Boyle's law, Charles' law and Avogadro's law strictly is called an ideal gas. Such a gas is hypothetical. It is assumed that intermolecular forces are not present between the molecules of an ideal gas. Real gases follow these laws only under certain specific conditions when forces of interaction are practically negligible. In all other situations, these deviate from ideal behavior. You will learn about the deviations later in this unit. Ideal gas equation. The three laws which we have learned till now can be combined together in a single equation, which is known as ideal gas equation. क्या है? At constant temperature and N, that is number of moles, V is directly proportional to 1 by P. ठीक है, या फिर प्रेशर इज इनवर्सली प्रोपोर्शनल टू वॉल्यूम, बॉल्स लॉ. At constant pressure and number of moles, volume is directly proportional to temperature, Charles' law. At constant pressure and temperature, volume is directly proportional to number of moles, Avogadro law. Thus, volume is directly proportional to the temperature, directly proportional to the number of moles, and inversely proportional to the pressure. फिर प्रोपोर्शनैलिटी साइन हटाने के लिए हमारे पास क्या आ जाएगा, कांस्टेंट आ जाएगा. तो यहाँ पर हमने आर ले लिया एक प्रोपोर्शनैलिटी कांस्टेंट. वी इज इक्वल टू आर एन इंटू टी बाय पी, where R is proportionality constant. On rearranging the equation, we get PV is equal to nRT. ये तो सबको याद होगा, PV is equal to nRT. और फिर R निकालना हो तो PV upon N by T, NT, sorry, PV upon NT. R is called gas constant. It is same for all gases, therefore it is called universal gas constant. Equation 5.17 is called ideal gas equation. Equation 5.18 shows that the value of R depends upon unit in which pressure, volume and temperature are measured. If three variables in this equation are known, fourth can be calculated. From this equation, we can see that at constant temperature and pressure, n moles of any gas will have the same volume, because V is equal to nRT upon P, and nRT and P are constant. This equation will be applicable to any gas under those conditions when behavior of the gas approaches ideal behavior. Volume of 1 mole of an ideal gas under STP conditions आप लोगों को पता है, ठीक है. वैल्यू ऑफ R for 1 mole of an ideal gas can be calculated. तो आप लोग डायरेक्टली देख सकते हो क्या हो जाएगा, 8.314 जूल Kelvin inverse mole inverse. At STP conditions used earlier, 0 degree Celsius and 1 atm pressure, value of R is 8.20578 into 10 raised to minus 2 liter atm Kelvin inverse mole inverse. Ideal gas equation is a relation between four variables and describes the state of any gas. Therefore, it is called equation of state. Let us now go back to the ideal gas equation. This is relationship for simultaneous variation of the variables. If temperature, volume and pressure of a fixed amount of gas vary from T1, V1 and P1 to T2, V2 and P2, then we can write directly equation हमें पता होना चाहिए कि P1 V1 upon T1 is equal to P2 V2 upon T2. ठीक है, ये equation खाली हमें पता होना चाहिए. Equation 5.19 is very useful equation. If out of 6 values of the 5 variables are known, the value of unknown variable can be calculated from the equation. This equation is also known as combined gas law. So combined gas law क्या है, P1 V1 upon T1 is equal to P2 V2 upon T2. ठीक है. Okay, density and molar mass of a gaseous substance. तो सिंपली अगर आपको डेंसिटी निकालना है तो आपको क्या पता होना चाहिए, यहाँ पर देखो डायरेक्टली इक्वेशन दिया हुआ है. m, like on rearranging equation we get the relationship for calculating molar mass of a gas. तो molar mass m is equal to d into r into t upon p. ये फाइनल इक्वेशन पता होना चाहिए. मोलर मास निकालने के लिए क्या पता होना चाहिए, डेंसिटी, गैस कांस्टेंट, टेम्परेचर एंड प्रेशर, बस. Dalton's law of partial pressures. The law was formulated by John Dalton in 1801. It states that the total pressure exerted by the mixture of non-reactive gases is equal to the sum of the partial pressures of individual gases. That is, the pressures which these gases would exert if they were enclosed separately in the same volume and under same conditions of temperature. In a mixture of gases, the pressure exerted by the individual gas is called partial pressure. Mathematically, P total is equal to P1 plus P2 plus P3 at constant temperature and volume, where P total is the total pressure exerted by the mixture of gases and P1, P2, P3, etc. are partial pressures of the gases. Gases are generally collected over water and therefore are moist. Pressure of dry gas can be calculated by subtracting vapor pressure of water from total pressure of the moist gas, which contains water vapors also. Pressure exerted by saturated water vapor is called aqueous tension. Aqueous tension of water at different temperature is given in table 5.3. Pressure of a dry gas is equal to pressure total minus aqueous tension. Partial pressure in terms of mole fraction. ठीक है, पार्शियल प्रेशर अगर आपको निकालना है इन टर्म्स ऑफ मोल फ्रैक्शन तो डायरेक्टली आप क्या पता होना चाहिए, P1 इज इक्वल टू N1 RT अपॉन V, मतलब ये हमें पता है P2 भी N2 RT अपॉन V, P3 N3 RT अपॉन V. तो डायरेक्टली जो आपका फाइनल इक्वेशन आता है ना वो ये है, वेर P1 इज इक्वल टू मतलब partial pressure and mole fraction will be the pressure, total pressure applied on the gas. तो P ये जो फाइनल इक्वेशन देख रहा है 5.29 PI इज इक्वल टू XI P टोटल. ठीक है, where PI and XI are the partial pressure and mole fraction of the ith gas respectively. If total pressure of a mixture of gas is known, the equation can be used to find out pressure exerted by individual gases. ठीक है, सो हियर आई स्टॉप. ये जो काइनेटिक एनर्जी एंड मॉलिकुलर स्पीड है ये टॉपिक हम लोग डिस्कस रीड करेंगे इन पार्ट 2 ऑफ दिस वीडियो. ठीक है, एक मैं आपको एक रिमाइंडर देना चाहूँगी या फिर एक सजेशन. देखिए आप डायरेक्टली ना ऐसे ये खाली अगर रीडिंग तो ऑफकोर्स आपको पता होना चाहिए कि एनसीईआरटी में क्या लिखा हुआ है, लेकिन आपको कॉन्सेप्ट भी पूरा अच्छे से पता होना चाहिए. यू शुड बी एबल टू सॉल्व सम्स, क्योंकि फिजिकल में ज़्यादातर क्या पूछते हैं, सम्स पूछते हैं. स्टेटमेंट वाइज बहुत कम आता है या मतलब नेग्लिजिबल है. हार्डली आपको 1-2 क्वेश्चंस दिखेंगे, 3-4 क्वेश्चन मैक्स उतना ही दिख जाएगा. तो मेन आप पकड़ किस पे बनाओ, अपने सम्स पे. और डायरेक्टली एनसीईआरटी रीड मत करो, पहले पूरा फिजिकल हो जाए, पूरा फिजिकल केमिस्ट्री अच्छे से पढ़ लो, पूरा मतलब सारे जितने भी फिजिकल केमिस्ट्री 11th-12th के चैप्टर्स हो जाए, उसके बाद आप एनसीईआरटी आओ रीड करो. वो भी इंपॉर्टेंट लाइन्स ही, ऐसा नहीं है कि पूरी टेक्स्ट बुक इंपॉर्टेंट है फिजिकल केमिस्ट्री की, नहीं. कुछ स्टेटमेंट है जो इंपॉर्टेंट है, वो आप रीड करोगे तो आपको खुद भी पता चल जाएगा, और क्लास में टेस्ट दे रहोगे तो आपको खुद भी समझ रहा होगा. तो ये थोड़ा सा एक एडवाइस देख लो, ले लो. एंड आई होप कि आप लोग सब लोग का पेपर अच्छा जाए. ठीक है, टिल देन इफ़ यू लाइक द वीडियो सो प्लीज़ हिट द लाइक बटन, सब्सक्राइब टू द चैनल, कीप स्टडिंग. थैंक यू सो मच फॉर वॉचिंग. बाय बाय.